Swayam Prabha. Digital India. Educated India.
We are discussing particle in a 1D box and we have succeeded in so far learning about the wave functions of a quantum particle in a 1-dimensional box. And the wave functions have turned out to be sine waves, and we have seen that only some will be allowed. The wave function that we have established so far are psi of x is equal to root over 2 by L sine n pi x by L, where n equal to 1, 2, 3, 4, so on and so forth, positive integer. And we have established that this set of wave functions, well, we have normalized, that is how we got root 2 by L. We have also established that they are orthogonal to each other, that is where we stopped in the last module. And we have also shown that the first derivative is not continuous at x equal to 0 and x equal to L. So, that really is not such a stringent condition on a wave function. The next step is to understand what are the energies. Since only certain wavelengths are only certain wave functions are allowed, only certain energies will be allowed as well. So, let us see how we get to that. This here is the expression for energy for a free particle, if you remember, and this is the energy that our particle would have as long as it is inside the box, and it can be only inside the box, E equal to h cross square k square by 2m. But then we have also learned from the boundary condition that psi must vanish at x equal to L, that KL is equal to n pi and n is a positive integer. So, the obvious next step is to take this KL in equal to n pi expression and plug it in to the energy expression of a free particle. The moment we do that, the energy expression becomes E of n is equal to n square h square by 8 ml square, where n is a positive integer. What just happened? Well, quantization of energy happened. Now we are saying that only certain values are allowed, and now we should say something that we deliberately did not say while discussing the wave functions in the last module. What is n? N turns out to be a quantum number for the particle in a box, and this is the beauty of Schrodinger's treatment. Unlike Bohr's treatment, where the quantum numbers fell from the sky, quantum numbers arise naturally simply from the probabilistic interpretation of the wave function provided by Max Born. Here we see an example of energy. Like energy, other quantities like momentum, angular momentum, these are also quantized, and everything arises from the imposition of some boundary condition or the other. So, now we learn a very important lesson in quantum mechanics. We learn that quantization finds its origin in the boundary conditions, which we know arise out of Born interpretation. This is very important to understand. I have seen many students who have got MSc in chemistry, good marks and all, and they can do the math associated with quantum mechanics. But this very fundamental concept has sometimes not sunk in. Let us all be very clear about this. This is one of the founding tenets of founding principles of quantum mechanics, that quantization really arises out of boundary conditions. The moment that happens, we can breathe easy. Now our conscience is clear. We have not imported a quantum number from anywhere just to satisfy some experimental observation somewhere. It has arisen naturally out of boundary condition. This is a great revelation, but that is not all. What we see in particle in a box is that, look at the energy ladder, the separation in energies increases as you go higher and higher up. Okay? That is one thing. The second thing is another important observation, a zero energy is not possible, because the smallest value of n, the quantum number, is 1, and for that energy has a value of h square divided by 8 ml square, which is non-zero. This brings us to the concept of 0 point energy, and this is something that becomes a governing factor when we discuss simple harmonic oscillator. We find that a free particle, a quantum free particle, can never be at rest, and it can never be at rest because if it is at rest, it is going to violate uncertainty principle. Let us say it comes to rest, it would have come to rest at some position. So, x is defined precisely, delta x is 0, and since it has come to rest completely, the momentum is also 0, plus minus 0. So, delta x into delta px is 0. That violates uncertainty principle. Uncertainty principle, we are going to talk a little more about uncertainty principle later on when we take a break from this quantum mechanical systems and discuss the operators and demonstrate uncertainty principle nicely using the position and momentum operators. But then the thing is, uncertainty principle is a law of nature. It is a boundary beyond which one cannot probe nature. So, it is not a question of making a better equipment that will let us see something we cannot see today. We can never do it as far as the current understanding of quantum mechanics is. You cannot do better than the best. You cannot violate uncertainty principle, and that is why a free particle can never be at rest, because that would violate uncertainty principle, since it would be associated with zero uncertainties of conjugate properties. That is another important revelation from particle in a box. Right. Now let us talk about the energy gaps between successive levels. What about that? If we take any energy gap, well, right now it is EF minus EI. So, NF square minus NI square. Let us say I take NF square to be NI square plus 1. We can work out what the gap will be. Let us keep it simple. Let us say n equal to 1, n equal to 2. 2 square is 4, 1 square is 1. Whatever it is, no matter which pair of quantum numbers you take, you get a constant. For that constant, what is the value of h square by 8 ml square if I change L? If L is increased, since L square is in the denominator, energy gap between the two chosen energy levels is going to decrease. Larger the box, smaller is the energy gap. Actually, I should not have written h nu here, that should come after another piece of discussion that we have coming up. But well, bear with me until then, we are really talking about the energy gaps. So, if L is small, then energy gaps are larger. If L is large, then energy gaps are smaller. What does that mean? If you keep on increasing the size of the box, the energy levels keep coming closer and closer and closer. So, beyond a certain value, the energy levels will come so close to each other that you cannot tell between this energy level and the next one. So, you do not have discrete energy levels anymore, rather you have a band. That would be the classical limit. So, this is another beautiful thing that comes out of our discussion. Just by changing the dimension of the box, one can go from quantum world to classical world and back, and it makes perfect sense in both the worlds. This is another point of strength, another reason why we gain confidence in this treatment. Now comes the discussion that should have come before I could write H nu. Let us talk a little bit about the spectroscopy. So, what is spectroscopy? Spectroscopy is the interaction of radiation with matter, and essentially it involves transition from one energy level to the other. And to be honest, we are not spectroscopy is something that is not at all new to us, because after all quantum mechanics is something that has sort of arisen out of spectroscopy. I am deeply indebted to a colleague who many years ago told me that spectroscopy is just quantum mechanics in action. All these calculations that we do in quantum mechanics is manifested in interaction of radiation with matter, because that is the only way in which you can probe the energetics of a system experimentally, and quantum mechanics is all about the energy levels and wave functions and so on and so forth. Now see, just because there are two levels, it does not mean that a transition will necessarily take place. In spectroscopy, something that is very important is selection rule, and selection rule, which tells us which transitions are allowed and which transitions are not, arises from something called transition moment integral. Transition moment integral is integral psi 2 mu psi 1, and the condition is that this transition moment integral must be non-zero. Now I think we might have introduced this nomenclature earlier as well, but just to make sure, in case we have not, let me just do it once again. What we have written here is this. In Dirac's notation, this is called Ket vector, Bra vector, and when we write a wave functions inside it, let us say I write psi 2 in a Ket vector, Bra vector, it essentially means psi 2 star, complex conjugate of psi 2. Of course, in our case we do not really have to worry about complex conjugates, because our wave functions of particle in a box are all real. This is Bra vector. If you write like this, so this is psi 1 in what is called Ket vector, and what it essentially means is you can just write psi 1 itself. A lot of complicated discussion becomes simpler if one uses bracket notation. In our case it is almost trivial, we might as well write the integral, but it at least saves us the hassle of writing d tau and all that all the time. So we will use bracket notation, but I should tell you what this means, what we have written here. When you write like that, so when you write Bra psi 2 Ket psi 1, then it essentially means integral over all space psi 2 star psi 1 d tau. In our case d tau should be replaced as dx, because we are working in one dimensional space. Now one more thing, it is possible that I might want to multiply this psi 1 by something or make some operator operate on something. What we have done is that we have used the operator dipole moment operator, which means basically multiplication by dipole moment. So this is what it means, but you might notice that there is an additional vertical line after mu like this, that is just to make things look good. It still means Bra psi 2 Ket psi 1 Ket mu psi 1, this is what it means. This is your transition moment integral, and the condition for transition moment integral is for transition moment integral to be non-zero is what we have to determine if we want to know which transitions take place and which transitions do not take place. For that purpose we are going to use here the property of symmetry of wave functions. One can of course plug in the expressions for wave functions and do it the hard way, work out the integral, and that has to be done many times. But many times you do not have to go through all that hassle. Symmetry is a fundamental property of systems which determines many of its aspects. So, here we will see how nicely one can use symmetry arguments to determine whether this integral is 0 or not. Remember, we do not really need to know at this point whether what the value of the integral is. If that is what we require, then of course we have to work it out. But if you only want to know whether it is 0 or non-zero, we will see how we can do it nicely with symmetry. To do that, let us first recognize that all these wave functions where n is odd, this one or this one, n equal to 1, n equal to 3, these are symmetric with respect to inversion. What is the meaning of symmetric with respect to inversion? If I say this is psi 1, right. So, I write something like this psi 1. And then I invert it. So, I interchange 0 and L in this case, let us say. Then upon inversion it will remove psi 1, it will remain psi 1. That is the definition of being symmetric or what is called an even function. However, look at this n equal to 2 or this n equal to 4. What happens if I interchange 0 and L? The function is going to change shape, right. Now this is plus psi 2. If I interchange 0 and L, you are going to have a function that essentially will look like this. So, upon inversion, what happens for n equal to 2, 4 etc., where n is even, we get psi n becomes minus psi n, and that makes it antisymmetric with respect to inversion, and such functions are called odd functions. Let me digress a little bit and point out that the number of nodes, remember what nodes means, node means a point where the wave function go through 0 and change sign. So, this is not a node, this is. So, number of nodes is n minus 1. When n equal to 1 there is no node, number of nodes is 0. When n equal to 2, number of nodes is 1. When n equal to 3, number of nodes is 1 here and 1 here. So, that is something that is just there, we should know it. Now, coming back to our original discussion, how do we know whether this integral is going to be 0 or not? Well, let me write on this side so that I do not have to erase it later on. See, an integral is non-zero when let me call this I, the integrand, this one is I. So, what happens if I changes sign upon inversion? So, let us say upon inversion I becomes minus I. What happens to the integral? The integral is I d tau over all space, that becomes minus I d tau. But the issue is we are talking about a transition between two levels that cannot change depending upon which one we decide to be, which point we decide to be 0 and which point we decide to be L. Just upon inversion the sign cannot change, right. So, when will this happen in any case? If this is equal to this, we are saying that the integral cannot change upon changing sign. So, that means integral I d tau must be equal to minus integral I d tau must be equal to minus integral I d tau. When will that happen? When both are equal to 0, is not it? Say q equal to minus q only when q is equal to 0, otherwise it is impossible. So, what we learn is that this I has to be symmetric, and I here is a triple product, two wave functions and your dipole moment. Is dipole moment symmetric or is it antisymmetric? Let us not forget that we can write dipole moment as mu equal to E into x, where E is electronic charge, x is displacement. X, is it symmetric or is it antisymmetric? Well, we have said this already, that a symmetric integrand is required for the integral to be non-zero. We are now asking the question, what about x? Is it symmetric or is it antisymmetric? What happens when we invert? X becomes minus x naturally. So, x is definitely antisymmetric. So, now when will this triple product be symmetric? So, we are doing inversion, right. We take this and do an inversion. When we do an inversion, x changes sign, x becomes minus x. Let us say psi 2 is symmetric. So, psi 2 will remain psi 2. Now, if psi 1 is also symmetric, what will happen? Then this triple product changes sign, which means the integral changes sign, which means the integral is 0. How can one avoid it? Only when psi is antisymmetric. So, if psi 2 is symmetric, psi 1 would better be antisymmetric. Sorry for my horrible handwriting. Then what will happen is that due to x you have a minus sign, due to psi 1 also you have another minus sign, and the whole thing becomes plus. So, what we are saying is that if one wave function is symmetric, the origin or the destination, then the other, the destination or the origin respectively, has to be antisymmetric. That is the condition for the transition moment integral to be non-zero. That is the condition for the transition to be what we call in the language of spectroscopy allowed. So, the selection rule then is delta n equal to 1, 3, 5, so on and so forth. Why? Because if you remember the wave functions, alternate wave functions are symmetric and antisymmetric. N equal to 1 symmetric, n equal to 2 antisymmetric, n equal to 3 symmetric again, n equal to 4 antisymmetric once again. So, delta n equal to 2 can never happen. What happens if I want to go from say psi 1 to psi 2? Psi 1 is symmetric, sorry psi 1 to psi 3, psi 1 is symmetric, x is antisymmetric, psi 3 is symmetric. So, psi 1 x psi 3, the whole thing is antisymmetric. So, that integral vanishes and that transition is not allowed. Now, if you want to know where this transition moment integral comes from, that requires a little more of quantum mechanics. In fact, we have discussed it in some detail in an earlier course that we had floated in on NPTEL, a course on molecular spectroscopy, a physical chemist perspective. So, whoever is interested in knowing more about where transition moment integrals come from can go through those videos of the course, of that course, which are now freely available on YouTube, I believe. But for the purpose of this course, at least for now, we are going to take this transition moment integral business axiomatically and we are going to proceed from here. So, doing that, what we have learnt is that for a particle in a box, delta n has to be 1, 3, 5, odd to even to odd transitions are only allowed. Which means that you can have this transition 1 to 2, you can have this transition 1 to 4, but you cannot have this transition 1 to 3. Why not? Because as we said several times, 1 and 3 are both symmetric, making the triple product, which is the integrand of transition moment integral, antisymmetric. So, this is the discussion we wanted to have on spectroscopy of particle in a box, and this is what tells us which transitions take place and which transitions do not. With this background, we are now prepared to go ahead and talk about color, and we are ready to talk about whether or not there can be some application of this simple particle in a box in real chemical systems.